Start your notes for section 1.4, which is on inverse functions. So we'll start off with kind of a light definition. The inverse of a function f of x, written with this notation you see here, is the function that undoes f of x. So the way we would say this out loud is f inverse of x. That -1, it kind of looks like an exponent because it's up in the air like this, but when it's used in function notation like this, it's not an exponent. So this isn't to the -1 power. This only means inverse. And if we were talking about the inverse of g of x, for example, we would say g inverse of x and so on. All right, so I have a little kind of visual of what's going on here. So we have a domain and a range, just a bunch of numbers here, a bunch of numbers here. And f is a function that would pick up an input x and map it to some output y. And in that case, f inverse does exactly the opposite. So it's undoing what f did. So it would pick up the value y and map it back to the input x. So I have a couple of examples here to go with it. First is a comment about the points, like what this means for individual xy points. So if you have the point, I'm going to say AB as like stand-in for two numbers, but this is a specific XY point. So it's 3, 4 in this first example. If that is on the curve f of x, then the exact opposite point BA would be on its inverse. So for example, if the XY point 3, 4 is on f, then 4, 3 is on its inverse. We can also see the same thought written in function notation. So for example, if f of 2 is 7, that tells me that on the graph of f is 2, 7. So that means on f inverse, we would have 7, 2. So f inverse of 7 must be 2. It's just the exact opposite of what we're seeing there using the same rule from above. So these examples combined with this fabulous image I've drawn at the top here is a nice way to observe that the domain and range of f are the range and domain of its inverse. So the domain of f is the range of f inverse. And then the opposite is also true. So the range of f over here is the domain of f inverse. So eventually in class, we're going to be actually looking at formulas for what f of x would be and its inverse would be. And if I ask you for the domain and range of each, really you only have to do half that problem. Because if you have this domain and range over here, then you would just flip it and get the other two over here. Okay, so more on that later. For now, a new definition. If I go too fast, feel free to pause me. We have the definition of one-to-one. So we're only going to use this definition when it's already a function. Really, you could apply this to any relation, but we only care if it's already a function. Okay, so a function is one-to-one if each output corresponds to only one input. This is the exact opposite of the definition of function from a previous section. So a function has one output per input. Here we have one input per output. So what we want to avoid, so what makes it not one-to-one, is if you have two different x values that both map to the same y. Right, we've got a couple of examples to look at here. First, we have a formula, f of x equals x squared. It has f of x notation for the y because it's definitely a function. But this is actually not one-to-one. For example, if you plugged in x equals 2 or x equals -2, they would both map to y equals 4. So if there's even one occasion of that happening, two x's that go to one y, that makes it not one-to-one. Graphically, instead of doing the vertical line test for a function, we're going to do the horizontal line test. So if any horizontal line can cross our curve more than once, then that means it's not one-to-one. That's the horizontal line test. So because in this image here, I can cross it 3 times with this particular line, this is not one-to-one. And essentially what that's telling me is that there is one y value right here where this x value maps to it, and so does this, and so does this. So this is 3x values with the same y. So we're violating that definition. This third example here is 1-to-1 because any horizontal line you draw using this horizontal line test, it's only crossing it one time. Even though it gets really, really shallow over here, it's never perfectly horizontal. It's kind of implying an asymptote. So we're assuming you can only cross this graph with a horizontal line one time. Okay, so the reason we care about this definition of 1-to-1 is the definition we have way at the bottom here. So a function is invertible, meaning it has an inverse, if it is 1-to-1. So we'll be seeing questions in class that say, like, here's a function, either a picture or a formula, and they'll say either, is it invertible or does it have an inverse? Those are the same question. Is it invertible? Does it have an inverse? And what we're looking for is, assuming it's already a function, you're just testing if it's 1-to-1 like we did here. So as these three examples, this one and this one are not invertible, and this one is. And again, invertible just means it has an inverse. Now, this all seems fine until we start to think especially about this first example of the three, f of x equals x squared. So the inverse of this function totally exists. It's the square root of x, right? That would undo the square every time. So this brings me to my very last comment here, which is like, sometimes you can kind of force an inverse to exist by just restricting the domain of the function. So we can use the inverse of this equals square root of x, as long as we only consider x's from 0 and up, then it's perfectly invertible. It doesn't have this issue because you took out all the negative x values and so on. So when we pick up at this in class, we'll actually see more formulas where we're computing inverses, checking inverses, and occasionally having to restrict the domain like this.